So here we are in chapter 10, where we're going to start talking about main memory. And I hop around quite a bit in chapter 10 because really, for an introductory level course, which this is, I know I keep saying that, we really just want to understand some of the basics and concepts and some of the terminology that we use when we talk about main memory. So we're not going to get into the physics and the science and the math part of how this works so much as just some of those kind of conceptual ideas of how main memory works. So bear with me. I'll try to help you stay on track as we move through some of these sections. So if you have the book and you're following along with me, you know kind of where we are. But we are going to start right at the beginning, 10.1 with the introduction. And, you know, in this chapter, looking at that computer's memory and like the input and output systems, right? That main memory, this is our immediate access store. So in a lot of ways, this is like what a lot of people think is like the most boring part of the computer because it's just sitting there alongside that CPU and it's just storing data. It's just, right? So memory doesn't really appear to do anything very clever. And you'll never really hear people talking about their main memory with like the same kind of excitement that they discuss when they're like talking about their CPU and overclocking and how fast their computer goes, and it's so exciting. So, but I mean, it's necessary, right? Because our main memory just grabs data and holds on to it until either the cache requests it, as we learned, or someone turns off the power, because our RAM doesn't hold anything in it without there being a charge. So we're going to talk a little bit about some of the progress that's been made in memory technologies over the years and some of the problems and how we've overcome those. And again, we're going to hop around just a little bit, but also looking at some operating principles of like that immediate access memory, talking a little bit about the differences between static and dynamic classes of memory, as well as volatile and non-volatile memory, which is a term that we've heard before in our lectures. And so, in principle, right, a computer's memory is the easiest component probably to understand. It's the place where programs and data live. And again, in practice, a memory system is invariably what we would call non-homogeneous. It's composed of devices from DRAMs to hard disks that are fabricated with a wide range of technologies, and indeed spread in the performance of memory that divide all of those devices. It's wider than any other element in the computer system. So we have a lot of choice, we have a lot of technology to work with, and a memory component may hold just a few words, right? So it could be really small, or 100 gigabytes. And it may have a read time as short as 1 nanosecond, blazing fast, or as long as several seconds. And it may cost a few cents, or it may cost $1,000. So we're really all over the place when we talk about our memory. And because this is such a gigantic topic, right, encompassing different storage technologies, it's broken up in our chapter into separate parts, which is, again, part of the reason why I jump around, because some of this is relevant to students at your level and some of it is not. Now, one thing the book points out for us is this term dynamic, right? So when we talk about DRAM, which is those sticks of RAM that you put in your computer, right? That's dynamic random access memory. And that word dynamic, as our chapter explains, is rather misleading. So in English, the normal usage of dynamic implies like a positive, like even aggressive level of performance, right? When you say that someone's like being dynamic, you would think like maybe they're a very animated speaker, they're very aggressive, they're very vocal. So we have this positive kind of implication when we think about this word. But really, when we think about it in the terms of computers and what our DRAM actually does, it's in reverse. So really the way this works, data is stored as an electric charge, and that electric charge just kind of leaks away over a few milliseconds because we aren't using anything to hold it there. And so DRAM loses its data in a few milliseconds. That's why when you turn off your computer and you turn it right back on, sometimes, with certain devices, they'll say, wait 10 seconds. And really what you're waiting for is that charge to dissipate, data to leak away from our DRAM, charge to dissipate from capacitors, and actually reset everything. Data can be retained in the DRAM, but only by continually reading it before it disappears, and then we have to write it back. And so there's this constant process if you are wanting anything to persist in there. And so the term dynamic doesn't really fit. I like how the author talks about it should stand for drippy because everything's just constantly leaking out of there. So just like previously when we talked about performance, we can talk about memory performance as well. And memory performance has really increased pretty rapidly at a rate of about 7% over the last couple of decades. And we can see that in our figure, which shows this. And so processor performance has improved at a really remarkable rate of like 60% a year, which has really dwarfed our memory performance. And so what we end up with is a major bottleneck in the memory system versus modern processors. And that's some of what we'll look at in this chapter as far as, operating principles is, how does this memory interact with and interface with the processor and some of that, timing that takes place. But again, not getting too into the weeds of the technical details. So let's talk about principles and parameters, right? Basically, what is a memory system? And I don't want to get, again, too in the weeds of history here, but a memory device does basically exactly what you would expect it to do. It remembers data. And you can implement a memory by exploiting any property of matter that allows you to make a change and then later detect that change. And so a lot of computer books and computer science classes and stuff will tell you that the first memory systems were those punch cards that maybe you've heard about. They would take these like wooden cards to make rugs, jacquard rugs on the loom. And so, I mean, if you have no idea what I'm talking about, you can Google this. But all systems of writing, like Egyptian hieroglyphics to pen and paper, these are all memory systems. So when we talk about like what is a memory system, we're not even talking about specifically computers, but really it comes down to that range of physical properties that can be exploited to store data. And it's quite remarkable, right? As humans, we have figured out all kinds of ways in order to store our data so that we can pass it down from generation to generation instead of just spoken word, which, dies with the person. And so, right, we've all heard, right, echoes off the walls of a canyon. Few people would think that using an echo as the basis of a memory system would be valid, but we talk about in the late 1940s, these columns of mercury in tubes were used to store data basically as sound in motion. So at one end of the tube, data in the form of a sequence of ultrasonic pulses was transmitted down the tube, traveling at the speed of sound in mercury, which we can see there is about 1,450 milliseconds. When the sound reached the far end of the tube, it was then picked up by these transducers, it was amplified, and it was fed back to the other end of the tube. And this was a form of dynamic storage because the data was always physically in motion. And even today, glass delay lines are used in some television signal processing applications to delay the signal by a fixed amount so that we can actually better perform. So there's when we talk about like what is a memory system, like we can't get too hung up on the idea that we're just talking about computers. So in 1950s, 1970s, we started looking at how data could be stored as a magnetic field in these tiny beads, right? And so we had this magnetic material called ferrite core, which is where we get that term core memory that often sometimes crops up in computer literature. But today's hard disk drives still use the same magnetic phenomenon to store data. We haven't really changed anything about how that works because, well, honestly, magnetics you can kind of think of as, just it's a property of nature. And so we're not doing anything special to make that happen. And so because of its importance, this magnetic recording and everything really comes out in greater detail if you start to look at, how do we make optical drives and things like that as well. And so then moving from the mid-70s on, our semiconductor memory provided the standard form of main memory as that static RAM, or sometimes SRAM, or is the dynamic RAM, which the DRAM. And today, we only have like a small number of embedded systems that use static RAM. Most PCs that you're aware of probably employ somewhere between 2 and 48 gigabytes of DRAM. I would say, some of you probably have, probably 16 gig. If you've got like maybe a high-end gaming system, you maybe have 32. If you are running some kind of like super boss workstation where you do a lot of like graphics and video processing and stuff, not only do you have like probably a pretty good GPU, but you maybe even have 128 gigs of RAM. So it kind of depends. So if DRAM is the theme of this chapter, then the variations are provided by some of the newer forms of semiconductor memory. And so we have our semiconductor ferroelectric memory, which stores data as the position of an atom within a crystal. So we're starting to talk about things at the actual atomic level. And then our avonic memory, which stores data by switching a glass-like material between an amorphous state and a polycrystalline state. And so there's a lot of vocabulary that then allows us to describe memory systems and technology. So you don't want to get too hung up on these words. If you're not sure what some of these things are, like ferroelectric, please, by all means, Google them so that you can get a better idea of what we're talking about. So we've talked about this idea of like dynamic RAM and things like that. So we're going to talk about this random access and sequential access type memory because it's a fundamental distinction that we need to make between the various types of memory technologies used in computers and the way in which data is accessed. So memory that is directly accessed is called random access memory, and that's where we get that RAM acronym. Because you can access any data element at random, and the time taken to perform the access is constant and effectively independent of the physical location of the data. So if we want to think about this a little differently, and I know sometimes some of us are familiar enough with the hardware we can actually like picture the little stick, but if it makes more sense, my first computer science instructor described it like a shopping cart. So you're at the grocery store and you have a shopping cart, and as you walk through the aisles, you can pick things off the shelf and you can put it in that shopping cart. Now, for the purposes of our example, we're going to decide like everything we're picking up fits in the cart, right? So we're not trying to put anything in there that's weird or doesn't fit. But as you walk through the aisles, you can put things into the shopping cart. Maybe you decide you don't want things anymore, you can take them out of the shopping cart. I do not have to pick up the bread and put the bread away before I can pick up the pasta sauce and put the pasta sauce away. There's no prerequisite order to how I can access items inside of the cart. And so when I get up to the checkout line, I can choose any order I want to start pulling things out of that cart to put them on the belt. And just like I put them into the cart in any order that I chose, and going back to that access time, it didn't matter if I was putting an item in or if I was taking an item out or what item it was, it always took the same amount of time. And so when we talk about this random access memory, that's what we're talking about. So sequential access memory is a little different. It requires us to access each memory element in turn until you locate the item that you are seeking. So this does have a prerequisite order to it that you have to follow, and you have to take things in the order that they are presented. So an example of this is a magnetic tape that we might use for storage. We have to read the tape to find the item that you want. Now, I know a lot of you maybe have never actually set eyes on a magnetic tape, right? A really long piece of ribbon in which data is encoded on it. It's got the two little wheels so that you can spool it from one end to the other. And so if there's a piece of data on there that's about a third of the way into that spool, I can't just jump to it. I have to wind that tape all the way to the point where I can find it, and then I can read that piece of data. And so they talk about the acoustic mercury delay line memory, right, mentioned earlier in the chapter. It is also a form of sequential access memory. So in comparison, random access memories are invariably faster than sequential access memories because I can go right for what I want. I don't have to go dig through everything else to get there. But they're much more expensive. Of course they are. And most semiconductor memory, like our DRAM or flash memory, is random access because otherwise our computers would not operate nearly as fast as we need them to. And that shift register that we've previously learned about is that serial access registry. And so we often talk about this idea of speed, right? We talk about how fast or how slow it is. And really these terms just refer to how long it takes to access the data. And so we could have a key parameter of memory, like its access time. And this gives us basically a benchmark when we start talking about performance of how fast it takes, how long it takes to access something when we talk about speed, right? How fast or how slow it is. So then two other terms we want to compare: volatile and non-volatile memory. And so if you store data in an ideal memory, right? Ideal being just kind of like best case, it stays there until you explicitly modify it. And such memory is called non-volatile. It doesn't change, right? Volatility being to change. So for example, when you write data on your hard disk, whether that's that solid state drive or that's your magnetic spinning disk, the data is going to remain on that disk basically indefinitely. And so some memory technologies allow us to retain stored data only as long as they receive electric power. So you pull the plug and it's gone. And these memories are said to be volatile because the data just evaporates in the absence of power, right? It just leaks out because we're literally talking about electrical charges on a surface. And yeah, they just dissipate. So the main stores of most PCs and workstations are that volatile DRAM memory, but of course we use that non-volatile hard disk storage to put our programs and our operating systems and things like that. So, I mean, you can kind of a thought experiment here, right? If memory were non-volatile, you wouldn't have to boot the computer, right? Which is transferring the operating system from non-volatile memory on disk to the volatile memory within the computer. Each time we switch the power on, everything would just be here and ready to go and much faster because, of course, accessing our DRAM is much faster than accessing our hard disks. But going back to our solid state drives, that's really where we're starting to bridge the gap because those solid state drives are giving us a closer level of performance to our DRAM than we were getting with our magnetic spinning drives. So then talking about read-write versus read-only memory. So if you can write data into memory or read data from memory and perform both of these operations in approximately the same amount of time, the memory is said to be read-write memory. And of course, the computer's main store is composed of read-write memory because we're constantly putting values in and we're getting values out. The memory can be easily read. Its contents, what we put in there changes often, right? So we're using this read-write memory. So in contrast, if you can only put stuff in, if you can only take stuff out, if you can only read, but you can't put stuff in and you can't modify what's there, then it's read-only memory. And so read-only memory is then invariably non-volatile because it doesn't change. So there's really no true read-only memory because, of course, you had to write something there in the first place. I know sometimes it's hard to think of that, right? There's no way to create just read-only memory without having to have made it volatile at some point. If there were, it would be impossible to create it, right? So perfect read-only memory would only be in the same position of like the perfect solvent that can't be stored in a container without dissolving it. So data is loaded into this masked program ROM at the time of its manufacture, and because the physical structure of each memory cell determines whether it holds a 1 or a 0, this masked programmed ROM, it's cheap in volume, but it cannot be modified later. So you can use it to hold what are called bootstrap loaders, operating systems like the BIOS that you might be familiar with, that runs your motherboard. So things that are kind of been rendered obsolete by flash memory, but practical read-only memory is really just best described as read-mostly memory. So like, you don't touch it very often, where it can be modified maybe a limited number of times, and it requires a more complex and slower write operation than a read operation. So we get those examples of this in what we call EEPROM flash memory. EEPROM stands for Erasable and Electronically Programmable Read-Only Memory. And so most memory, going back to, is read-write, and read-only memory, like true read-only memory, doesn't really exist. But we do have these systems where, something was written to this little bit of memory, we use it for a specific purpose, but we never change or really modify anything on there, or maybe only do so sparingly or a certain number of times. So the last comparison we're going to make is static versus dynamic. So we have our random access, read-write, and volatile memory, and these can be divided into our two subclasses, static and dynamic. And these classes refer to the structure of the semiconductor memory cells and their properties. So static memory uses and I know it might be hard to understand this if you maybe aren't, haven't taken like an electrical course, but they are cross-coupled transistors that create an RS flip-flop that stores the data in the state of the flip-flop. Whereas dynamic DRAM employs a semiconductor technology that stores data as an electrostatic charge in a capacitor. So static memory is faster, it's more expensive, it's less dense in that we have less bits per chip than the dynamic counterpart. So dynamic memory is much cheaper than static memory, but it's more difficult to use in actual circuits. Now, as we progress with things, that statement is less true today than it was in the past, because nowadays DRAM control is built into CPUs, and we have things like motherboard bridge chips and then built into the DRAM themselves, like we're literally putting controllers on there to help them be smarter. And so if we think back to like the 1980s, building a DRAM controller into your computer was like a super daunting task, and it would have been extremely expensive and really wouldn't have been something people did. So the data in a dynamic memory cell is lost after a few milliseconds unless it continually is rewritten in an operating system process called refreshing. So dynamic memory has different read and write access times, and typical DRAM is not truly random access because adjacent memory cells are faster to access than cells that are then selected at random. But because DRAM forms the bulk of most PCs and workstation memories, the performance and characteristics of DRAM strongly determine the overall performance of our computers, and that's why we talk about it kind of in greater detail and we want to understand how it works. So let's talk a little bit about memory parameters. The smallest unit of memory that we can have is the memory cell that stores a single bit. So we're just talking about a 1 or a 0. And so semiconductor memories are composed of an array of n rows by m columns. And so we can say they contain n times m cells. And the width of the memory, which is m, is the number of bits per word in the memory. So when a read or write operation is executed, all m bits of a word take place in the operation simultaneously. The length of the memory, which is that n value, is defined as the number of addressable locations. So we have some terms in here, like width. And so the width of the memory component It's not necessarily the same as the width of the bus or the width of basic data units in the computer. So, for example, a computer may have a 64-bit data bus and a 4-bit wide memory components. And so this arrangement then requires 64 divided by 4, which is 16 memory components arranged side by side. And so they span the 64-bit data bus. And because each memory component contributes 4 data bits, if each 4-bit memory device has 4 M uniquely addressable locations, then we could say that the memory device has a capacity of 4 bits multiplied by 4 M locations, right? That's megabits. So that we would get 16 megabits, right? That's 2 to the 24 bits, or 2 megabytes, right? Big B, megabytes. And that's one thing I want to make a distinction here. And I sometimes talk to students about this when we're talking about internet speed. So bits, right? We've talked enough about bits. Hopefully we know what bits are, versus megabits, right? So that's little b. When you have M little b, we're talking about megabits, versus M big B, we're talking about megabytes, right? So remember the difference between a bit and a byte. And so there's clearly a difference between a megabit and a megabyte. So really, 1 megabit is 1 million zeros and ones, right? So a megabyte, right, big B, is 8 million zeros and ones. And that gets confusing. And I know, and I have this conversation with students when we start talking about internet speeds, because sometimes your internet provider will give you speeds in gigabits, not gigabytes. Clearly, there's a difference. So we have a good figure here, figure 10.2, which illustrates a little bit how this width can be used. So if that previous explanation was just a little nebulous, hopefully you could take a look at this figure and kind of get an idea of what we were talking about. Again, we're not going to get too deep in the weeds on how this stuff works. And at this point, we're going to hop ahead into section 10.2.1 and talk a little bit more about static RAM. So not to get too deep in the weeds about static RAM, this is an idea of how it works conceptually. So we have 2 inverters, and they're connected end to end in like a little ring, right, in a circle. So input to gate 1 is the output to gate 2. And so you literally can just see how things can follow around and round in this circle. The input to gate 2 is the output from gate 1, thus the input to gate 1 is fed back to produce the input of gate 1. Okay, so we call this a self-sustaining memory element, because whatever state the input to gate 1 is in initially, the state is fed back to maintain itself. So that we call this a cross-coupled circuit, and is essentially the same as the RS flip-flop that we talked about way back in chapter 2. Now, we talked a little bit earlier about how static RAM, right, it's less important than it once was because of, we have this simpler CPU interface than DRAM, and it was once the memory of choice for particularly small computer systems. But static RAM, it can retain data in a powered down mode using a small battery. So that's why we see on today's motherboards, they take those nice little small watch batteries. And so your motherboard has the BIOS, which is the basically the operating system for your motherboard, tells everything how to work when you don't have something like Windows installed. And that way it retains that memory in static RAM by using the power of that little battery. But again, it's of less importance to the design of larger systems because the economics of our DRAM-based memories. But because static memory can be very fast, we can use it to fabricate cache memories, or like going back, as early as 1981, there were like these experimental static RAMs with access times as low as 0.6 of a nanosecond, right? That's blazingly fast using some different types of materials other than silicon. But it's not to say that it's not used. It's not to say that it's not important. It's just not as important. But it's still good to know that it exists and the differences. So if you are super interested and you want to learn all about how static RAM works, please go ahead and finish section 10.2. But we're going to hop ahead to section 10.3 and talk about DRAM. Because again, DRAM is what most of our PCs and workstations are implementing in their main memories. And it's played a key role in the development of high-performance computers, where its operating parameters are continually changing as new variants are developed. So an understanding of DRAM is necessary to appreciate where computers are headed in the near future. And so in this section, we're going to look a little bit at, DRAM's operating principles and some of those things. But again, we're not going to dig too deep into the weeds here. So the operating principle of our dynamic random access memory, it is pretty simple. Data is stored in the form of an electrostatic charge, and it goes inside of a transistor. And when a material is uncharged, the number of electrons in the material equals the number of protons. So negative electrons cancel out the charge on positive protons, and there's no overall charge. So we have just nothing. So when a material is charged, electrons are either added or they're removed. And if there are too few electrons, the charge is positive, and if there are too many electrons, the charge is negative. So information that we want to store can be stored a bit at a time as a charge or no charge on a tiny capacitor. And all we need is a means of writing the charge into the capacitor, removing it, and then detecting its presence or absence. And so that is how DRAM works. And really, if we look at this figure 1016, it kind of illustrates the basic principle of this field effect transistor from which most logic devices are fabricated. So we have this tiny region of doped silicon on a chip. It has two connections to a positive and negative terminal of a battery, right? And doped means that an impurity has been added to the silicon to supply some electrons that are free to carry a current through the silicon, because the electrons in pure silicon are bound to atoms and they can't move, which is one of the things that makes silicon so great for making like microprocessors. But we actually want the electrons to be able to carry the current. So they dope it. They put a little impurity in there so the electrons can actually do that job. So above the region of silicon that conducts the electricity is a conductor labeled gate. You can see that gate there in our figure. And we'll assume that this conductor is electrically insulated from the silicon channel through which the electrons flow between the terminals. And here we can see what happens when a negative charge is applied to the gate. The charge creates an electrostatic field that penetrates the silicon channel, and because the change from the gate is negative, the electrons on the channel are repelled away from the gate, like charges repel and unlike charges attract, right? Just normal magnetics. And so in this figure, the charge is so strong that the channel is said to be pinched off, and there's no current that can flow through the channel. So by putting or not putting a negative charge on the gate, the current flowing through the channel can be controlled. This ability to cut off the flow of electrons is used by all gates, and it's used by the DRAM and of a class of like the read mostly type memory, like our EPROMs. And that is essentially how it works. So in the chapter, they have this, I think this is a pretty great figure that illustrates the internal structure of a DRAM memory. And the most kind of significant point here to note is that there's not just like a single memory array. Commercial chips consist of typically 4 memory banks or arrays that we can see here. And so we can take a look at, we've got these address buffers, right? We've got a command decoder. We've got some various controllers. We've got a mode register. We've got these banks. And we can see and watch all these arrows as things move in and out. Now let's hop over to 10.3.1 and talk about DRAM timing for a second, because what I find really fascinating is that the timing of our classic DRAM from the 1980s, from which all modern variants are derived, still holds true today. The same formula that we figured out for timing of memory in the 1980s is exactly the way your stuff works right now. And some people might see that as a bad thing, but sometimes when you just make something and it works, you're not necessarily inclined to try to figure out another way. Now, I'm not saying that like it's not faster, it's not like we haven't made any improvements, but we really have to understand the nature of DRAM timing in order to then appreciate how successive generations have made everything faster. And so, right, although the nature of like this one transistor DRAM memory cell has not changed, if we take a look at our figure here, this represents kind of a simplified read cycle timing diagram of a basic DRAM chip. So we can assume 1 megabit by one organization, and right, then we have 2 to the 20 locations. So we have these address lines, A0 through A19, because there are 20 of them. From the CPU, they're fed into a multiplexer to select either one of our row addresses, so like A0 to A10 or A9, or A10 to A19, which is a column address. And then our 10 outputs of the CPU address multiplexer are connected to DRAM addresses A0 to A9. And so it kind of gives us a pretty simplified kind of flow chart of how things move. And then if we also look at the read cycle that lasts from A to B, we have this duration that takes place, and that's our read cycle time. And unlike static memory that has an equal cycle of access times, our dynamic memory has a longer cycle time than its access time, and DRAM can't begin a new access as soon as the current one has been completed because it performs a little internal operation known as pre-charging between accesses. So it can't just immediately take off and try to do the next thing because it does that little internal process. Now that's all I want to talk about as far as timing, because then it gets very math intensive. So we're going to hop over to 10.3.2 and talk a little bit about developments in DRAM technology. And really what I want to talk about, because we've kind of just talked about this plain, right, basic DRAM, but successive generations which have improved DRAM, right, and just talk a little bit about what modern DRAM looks like, especially from the point of, we want to talk about things from the point of a computer scientist, but also from the point of a consumer. Because just like when we talked about why CPUs end up being like the main point of marketing, when you're looking at a computer or you're talking about computers and you want to talk about RAM or storage or memory, then understanding what it is that you're talking about is also very important. So the first kind of radical change in DRAM technology occurred around 1997 with the introduction of what we call synchronous DRAM, which was termed SDRAM. And this uses a system clock of its own to perform, or it uses a system clock, not necessarily of its own, to perform synchronization, and incorporates a more complex interface that can receive encoded commands from the host processor. So it uses a combination of control signals to encode a command, so like read, write, or pre-charge, so it can basically control a little bit more about what was happening versus just sending those pulses. Now the access time for SDRAM is similar to that of other members of the DRAM family, but its burst access time was considerably shorter. And these control signals and commands are kind of latched onto the rising edge of the clock, which simplifies the design of a system, and then a control register in the SDRAM kind of defines its operational parameters, such as the burst length, the number of words accessed per read or write cycle. And so the SDRAM is basically a programmable device whose operational parameters can be adjusted to suit specific systems. So we started to kind of dial in a little better how to use these multiple memory banks that operate independently for best results. And one of the things I love that the book points out here is when we start to talk about speed, because speed is one of those things that we often talk about as a term of performance, especially when we are thinking about buying or evaluating a computer. And there's some confusion in the way memory standards for PCs are described. So you have this DDR SDRAM, and then you'll usually see it described as like PC 1600, PC 2100, 2700. This defines the bandwidth of the memory. SDRAM standards are written as like 66, 100, 133, which describes the clock speed of the SDRAM, which, as we should know at this point, are two totally different things. So if we have a DDR SDRAM clocked at 100 megahertz, then it's called DDR 200. And a system with a 64-bit data bus can transmit 8 bytes at a time to give a bandwidth of 8 times 200, which is 1600 megabytes, hence the designation of PC 1600. So when you see these kinds of designations, sometimes it does get very confusing, especially for consumers, to understand what are we talking about. Now, most people are like, big number is better, which is not a terrible way to look at things. But if you actually want to be informed about what these numbers mean and how to generally read them, then that's what we're trying to define here. So this DDR, right? What is this DDR DRAM? Well, DDR stands for double data rate. And really, it's a little different to conventional SDRAM in terms of its internal storage mechanisms. And the difference between DDR DRAM and SDRAM really lies in the interface. And so the DDR SDRAM performs a data access on both the rising and falling edges of the clock. So it delivers data at twice the clock rate, which, going back to our math, right? DDR SDRAM clocked at 100 megahertz is called DDR 200. So looking at this figure here, it kind of illustrates this read-write cycle timing, which ends up looking like this little interleaved set of risings and fallings. So once the first access of a burst has been made, data is available at each edge of the clock. So we have this parameter, CAS latency, or CL, which defines the time in clock cycles between the point at which the column address strobe is asserted and the point at which data becomes valid. Now, we know a little bit about data validity because we talked about this when we talked about processors. But really what it means is that we're accessing data at twice the rate. That CAS latency, which defines the time in clock cycles, we have this point in which our column address has been declared and is asserted, and when the data becomes valid. So there's that just basically a point in time as we read on both ends of the clock where we have this latency of, is my data actually valid? Am I ready to use it? So rising from this original idea of DDR DRAM, we started having DDR2, which took over and kind of peaked, and then we moved on to DDR3, and then DDR4 kind of waiting in the wings. So each of these variant technologies, right, and we know how fast technology tends to change, accompanied by new families of motherboard chipsets to interface them to the host CPU. And so they all operate just like a little differently, and of course, building upon these ideas of the rising and falling clock edge, taking that one step further to perform, in this case, 4 data transfers per clock cycle for DDR2. And so as things progress, we're just taking the same ideas and we are improving upon them so that we can try to get faster performance. So we can take a look at this table here to get an idea of some of our DRAM generations. So this table shows us the progress made by successive generations of DRAM, and starts with that DRAM, right, family name, its clock rate, except for, like our basic DRAM and the EDO DRAM, right, because it's not clocked. The data rate, assuming a 16-bit data bus, and the data rates are quadrupled for 64-bit data buses. So you can see here as things got progressively faster from our standard DDR to DDR2, DDR3, DDR4, DDR5, which exists now but not at the time this book was written, DDR6, which is already in the works and is 4 times faster than our DDR5. And so, we're constantly improving these memory standards, and we're getting to the point where we're almost bottlenecking up against what our motherboard chipset design can support. And if you'll go look at some of the upcoming ideas for DDR6 and forward, we may actually need to start plugging power directly into our memory modules in order to support kind of the higher level of support necessary for these new generation of memory modules. Now, briefly, I want to talk about flash memory, because I would imagine most of us have probably used some form of flash memory. Flash, which is the EEPROM type memory, and most people just call it flash memory, can be programmed and erased electrically and provides a really convenient means of storing like firmware and computers on our digital electronic devices, portable applications, and really it comes down to this structure of a flash memory cell. They get into the science a little bit about how these things work. I don't want to get into that too heavily, but I do want to talk about flash memory so that we understand a little bit about what this is about. So I say a lot of us have probably used flash memory, maybe in our cell phones, maybe we've used those little SD cards before in our digital cameras, or we've got those USB sticks. And so really 2 pillars of modern technology and computing are the USB bus and flash memory. And, I'll tell you, and I'm not even that old, when I was in college, we were still using floppy disks, and it seems like we accelerated really fast between floppy storage and flash drives. There wasn't very many stops in between there. And the USB bus, which we're not going to get into, really allows us to connect a wide range of digital systems together. So like our digital cameras, our cell phones, connecting those to our iPads and to our PCs with a very minimal amount of fuss. Our data transfer rate, the information exchange protocols are all handled automatically. They're basically invisible to the user. You do not need to understand how USB works in order to work it. And our flash memories have really grown from our 8 megabyte devices to flash cards that can hold like 512 gigabytes. You can buy these kinds of flash drives that combine the USB and flash technology, right? Those are those little sticks. You're plugging them into your computers. You're carrying around your files, right? So this continuous progress in flash technology is really what has led up to this introduction of our solid-state disk drives that we're seeing in laptops, replacing our hard disk drives that, spin, which is always going to be a problem in a moving computer, increasing performance. We have faster data transfer, access time, lower power consumption, better reliability. There's not a lot of vulnerable moving parts. And so flash technology really is where we're kind of headed. And we have this, these compact flash, because traditionally semiconductor memory components were available either in the dual inline packages that you have to plug into sockets or solder directly onto a PCB, or in tiny packages that were designed to be soldered onto boards by like automatic machinery. And so those packages can't be used in consumer applications. They require interoperability. And starting in, really it came out in 1994, compact flash memory cards. Those are those little SD cards, right? They come in a couple of different formats, right? Most people know them as the big and the small. But they were introduced to enable users to be able to plug memory into domestic and personal computer-based systems. And we see these in like, well, we used to see them in MP3 players, but now we're able to put enough storage in those things. Or we just use our phones, which again is using a form of flash memory. But I mentioned digital cameras because, I mean, digital cameras are still using this kind of flash memory. I have a dash cam in my vehicle and it uses a compact flash card. And so these memories, they're small. They're sometimes just a couple of millimeters thick, about half the size of maybe a quarter, right? They're tiny. And they allow us to, save data to them, copy pictures from our digital camera to maybe our laptop. They're available in a couple of different formats, right? That's the type 1, type 2, the big and the small. But the advantage of these types of modules is their high reliability, the lack of susceptibility to shock, so you can't really static charge them and lose your data, the low cost, and they were designed to support dual voltage standards, 5 volts and 3.3 volts, which makes them compatible with both modern systems and older systems. And they've been adapted for other functions in addition to flash memory. So you can get like micro drives and input-output devices for like Ethernet and Bluetooth wireless adapters. And, even if maybe you have a tablet or a cell phone that even takes an SD card, allows you to add some more storage. And the compact flash card interface, it's a host system, uses a 50-pin connector that's similar to like a PC card connector, which are the cards like your graphics card that you would put into your motherboard. And these interfaces, they have an external system. It's not a simple memory interface, so they've like consisting of a data and address and control lines. This interface, it provides a bus, which means the intelligence can actually be built into the cards, like real performance. And these intelligent controllers, they manage an interface protocol, the data storage, the retrieval, error correcting codes, diagnostics. They can use configuration registers, software management systems. And so from the point of view of the host system, like whatever you're plugging this card into, the card just looks like a standard disk interface, right? It can't tell the difference. And so this is really where, and then we get into like the memory stick, right? And Sony was one of the leading companies in the design of the little memory sticks, right? Flash drives or flash sticks or memory sticks, or no one seems to know what to call them. But they created their own standard for interchangeable memory and called it the memory stick in 1998. And the device has all of the attributes of a product aimed at the consumer market, right? It's compact, it's light, it's easy to carry, it's easy to handle, it's simple, it's reliable, and it can be made read-only to protect your data. And so while we started with those first generation devices in 1998 that had a capacity of like 64 megabytes and they were super expensive, I remember them being like $50. By 2002, we'd grown up to 512 megabytes. The price had come down considerably. Now you can get them like up to like 2 terabytes. It's crazy. And they haven't gotten any bigger. Like size-wise, they have not gotten any bigger. So really, this change in technology, this advancement, when I say that flash memory is the future, I really think that's where we're going. So that is the end of chapter 10 for us. And so, many computer users, and I'm just talking about general consumers, not computer people, because computer people probably pay attention to RAM, but computer users, just general consumers, probably know the difference between an Intel processor and an AMD processor, but they probably do not appreciate the difference between like DRAM and DDR3 and all of our different types of speeds and what those numbers mean. They may not equally be aware of the trends in memory system design and the increasing role played in new forms of this non-volatile memory. But we know, right, as computer scientists, that without memory, all of the fastest CPUs in the world would be useless, except perhaps as devices that can calculate the value of pi to thousands of decimal places. But Today, huge memories are required to hold the seemingly unended quantities of data required for multimedia applications, and we want low power memories for cell phones and portable applications, and non-volatile memories for MP3 players and digital cameras. And I know I hopped around a lot in this because this is a very technically heavy chapter. If you like that kind of thing, if you've got a little engineering, if you've got a little math, go take a look. I think it's super fascinating when we start talking about how things work at the atomic level. But really, we looked at the technology and organization of memory components used to construct our immediate access stores. So we've seen how semiconductor memory is even more affected by trade-offs in like speed, price, performance than maybe our processor technology. And we talked about a lot of terminology, right? We've discovered you can have non-volatile memory that retains its data when you switch the computer off, but you have to pay a large premium in terms of long-term, or pay more in the long term. I don't know where I was going with that, but we've seen that you can have low-cost, high-density DRAM, but you have to put up with longer access times than static RAM. You have to use more complex logic to control it. Static RAM is fast and easy to use. It's more expensive and less dense than DRAM, right? There's a lot of things to compare when it comes to memory. So hopefully this gives you kind of an overview of things that, when we talk about main memory, kind of how does it work? What are we talking about? What do these numbers mean? And gives you a little more conceptually an idea of how your memory works.